Hello everyone, let me introduce myself first. My name is Infantri Siahaan, mechanical engineering student at Udayana University, and now I want to presenting about heat treatment of non-ferrous alloys. The main reference I take from Metallurgi for the non-metallurgist second edition, and from Arthur C. Riordan. So the topic that we will discuss for this presentation is about recovery and recrystallization annealing, heat treatable aluminum alloys, cobalt alloys, copper alloys, and the other alloys that we will discuss. Okay, the first is heat treatment of non-ferrous alloys. Non-ferrous alloys are heat treated to tailor their properties for a variety of purposes, including aiding in recovery by reducing internal stress, promoting diffusion by redistributing existing alloying element, promoting new recrystallized grain formation, promoting grain growth, and the other, and which in the last is promoting new paste formation through the introduction of foreign atoms. Recovery and recrystallization annealing. Annealing is primarily a function of two main variables in non-ferrous alloys: the temperature to which the material is heated and the hold time at temperature. For steel alloys, the rate at which the alloy is cooled back down from the soak temperature is critically important factor during the annealing cycle, and the cooling rate may also be an important factor for specific non-ferrous alloys. When annealing is performed for short periods of time or at low temperature, the hardness of a cold work alloy remains relatively constant. This initial stage is referred to as recovering annealing. Cobalt alloys. This is the characteristic of cobalt alloys, such as strength and hardness. Cobalt alloys, such as stellite and cobalt, chromium, and molybdenum, are known for their exceptional strength, hardness, and wear resistance, making them ideal for applications that require high performance and long-lasting components. The high temperature stability. These alloys maintain their mechanical properties even at elevated temperatures, allowing them to be used in high heat environments such as cutting tools, aerospace components, and medical implants. 3 is corrosion resistance. Cobalt alloys exhibit excellent corrosion resistance, particularly in acidic and oxidizing environments, making them suitable for use in chemical processing equipment, marine application, and medical devices. 4 is biocompatibility. Some cobalt alloys, like COCRMO, are biocompatible, meaning they can be safely used in medical implants and prosthetic devices without causing adverse reaction in the human body. Next is copper alloys. So this is the example of copper alloys, I think, and brass an alloy of copper and zinc is known for its excellent corrosion resistance, machinability, and decorative appearance, making it a popular choice for hardware, plumbing, and architectural application. Bronze, an alloy of copper and tin, is prized for its high strength, hardness, and resistance to wear and corrosion. It is commonly used in statues, medals, bells, and other artistic and historical objects. 3 is copper-nickel alloys. Copper-nickel alloys, such as copper-nickel, exhibit excellent resistance to seawater corrosion, making them ideal for marine applications like ship hulls, propellers, and heat exchangers. Next is beryllium copper. Beryllium copper, an alloy of copper and beryllium, is known for its high strength, hardness, and electrical conductivity. It is commonly used in springs, connectors, and other high-performance applications. This is now topic about magnesium alloys. So this is the characteristic about magnesium alloys, such as lightweight, corrosion resistance, stability, and damping capacity. Lightweight, Magnesium alloys are among the lightest structural metals with a density about one-third that of steel or aluminum. This makes them ideal for applications where weight savings are critical, such as in the automotive and aerospace industries. 2. Corrosion resistance. Magnesium alloys can exhibit good corrosion resistance, especially when properly coated or protected, making them suitable for use in harsh environments and marine applications. 3. Castability. Magnesium alloys have excellent castability, allowing for the production of complex, near-net shape components, which can reduce manufacturing costs and lead times. 4. Damping capacity. Magnesium alloys possess good damping capacity, which can help to reduce vibration and noise in various mechanical systems, making them useful in applications such as consumer, electronic, and power tools. Nickel alloys. Nickel is an austenite former and no allotropic phase transformation occurs in nickel or the high nickel family of alloys. The alloys are austenite from the melting temperature down to absolute zero. Nickel has a natural tendency to combine with sulfur and or oxygen. It is found in nature as nickel sulfide and nickel oxide ores. In heat treating, nickel or nickel alloys is critical to minimize exposure to sulfur in solid, like lubricants and grease or gases from once embrittlement by sulfur occurs. The contaminated area must be removed by grinding or scraping. Nickel has very low solubility for carbon in the solid state, so it doesn't readily carburize. Titanium alloys. The response of titanium and titanium alloys to heat treatment depends on the composition of the metal and the effect of alloying element on the phase transformation of titanium. Like iron, titanium is an allotropic element. Titanium has an HCP crystal structure or hexagonal crystal and called alpha phase at temperature below 885 degrees Celsius. When the temperature of pure titanium reaches that temperature, called the B transist temperature of titanium, the crystal structure changes to a BCC structure, or body center cubic. The high temperature BCC structure of titanium is referred to as the B phase, which persists at temperature up to the melting point. Next, the last is other nonferrous alloys. The precious metal, including silver, behave somewhat similar to copper and nickel. The most important silver alloys are the silver-copper type. Copper is added to increase the hardness and strength of silver, while its effect on the electrical conductivity is small compared to that of other additions. Okay, that's the last topic about nonferrous alloys. So I just say thank you for your attention in this video and see you on the next presentation.